Hello dear students, I welcome you to lecture 12 of linear algebra first, unit first, system of linear equations and matrices. In last few lectures, we studied system of homogeneous equation and system of non-homogeneous linear equations and elementary matrices. Lecture we study properties of elementary matrices. Okay. In this lecture, we first preview our some definitions. Define elementary matrices corresponding to elementary operations. Define elementary matrices corresponding to elementary operations. We will see that the performing an elementary row operations on a matrix A is same as multiplying A on the left side by an elementary matrix E. We will see that any matrix A is invertible if and only if it is the product of elementary matrices. Definition. A square matrix A of size n by n is called an elementary matrix if it is can be obtained from the identity matrix In by a single elementary row operation. That means A is obtained by switching two rows on elementary matrix In or multiplying a row of In by a scalar C not equal to 0 or adding a scalar multiple of a row of In to another row. This definition tells you a square matrix A is called an elementary matrix if it can be obtained from the identity matrix In. First we say that elementary matrix I is equal to 1, 0, 0, 1 is elementary matrix I2, that is of matrix of order 2. This is identity matrix of order 2 by 2. Similarly, 3 is equal to matrix of order by 1 0 0 0 1 0 0 0 1. This is the element matrix of order by 3. Similarly, identity matrix 1 0 0 0 0 1 0 0 1 0 0 0 1. This is identity matrix for 4. We know that the definition of identity matrix is a square matrix whose diagonal elements is equal to 1. That is, identity matrix is a square matrix whose diagonal elements is equal to 1 and other elements are 0. That is, identity matrix is matrix whose is equal to 0. Ij is equal to 1. Ij is equal to for I is equal to whose diagonal elements is equal to 1 and all other elements are 0. This is the definition of identity matrix. So, In is equal to identity matrix 1 by n by 1 0 0 so 0 1 so 0 so that 0 0 is identity matrix of n by this is the In. Okay. A square matrix A is called an elementary matrix if it can be obtained from the identity matrix In by a single elementary row operation. That means A is obtained by switching two rows of In. Suppose this is I3 identity matrix of order 3 by 3. Element R's 1, 1, 0, 0, 1. This is by identity matrix. We form an elementary matrix A I3 by two rows of In. Okay, I3 that is the elementary matrix by performing one operation interchanging rows R1 and R3. Okay, R1 and R3. And we get 0, 1, 0, 0, 0, 0, 0, 1. This is the matrix obtained from I3 by interchanging row 1 and row 2. Similarly, we obtain an elementary matrix from I3 by multiplying R1 1 I3 by minus 3. Then we obtain an elementary matrix A as minus 0, 0, 0, 1, 0, 0, 0. This is an elementary matrix obtained from I3. Also, we obtain an elementary matrix adding row plus row 2. Row 1 R1 plus R2 we get matrix and 2 in R1 1 0 0 1 0 0 1. Matrix obtained from I3. This is the definition of our elementary matrix. Okay, this is a theorem for an elementary matrix. Theorem. This theorem says that if is elementary matrix, then E inverse exists and is elementary. That is, if is any elementary matrix, then its inverse E inverse exists and is elementary. And inverse is also as elementary. Okay. Proof for such each of the three types of elementary matrices, write down the inverse and check. I will do it on the book. Okay. We solve this by Okay. Suppose I is equal to 2 by 2 matrix 0 0 1 multiply or 2 minus 8 matrix as equal to 1 0 0 minus 2. Increment of E is equal to increment of 1 0 0 minus is equal to minus 2, and we know that E is equal to increment of E in is equal to minus into matrix 0 0, and this is the inverse E inverse, and this is equal to minus 2 upon minus 2, 0 upon minus 2, 0 upon minus 2, 1 0 0 minus then elementary matrix. This is also an elementary matrix. This this example elementary is an elementary matrix, then its inverse exists, and the inverse is elementary matrix. This is the proof of this by an example. this is an example. Let A equal to matrix 1 0 0 3 1 0 0 0 1. This is a 3 by 3 matrix. This is elementary matrix. Okay. This is the matrix elementary EPS Y. Answer yes. It is elementary matrix. The matrix A is obtained from I3 by adding 3 times the first row of I3 to the second row. Okay. This matrix A solution. Suppose I is equal to I is equal to matrix 0 0 0 1 0 0 0 1. This is an matrix I3 of order by multiply. Okay, we perform one operation on this. It is R2 plus 3R1. This is row operation on this. We know that this row first, second row. We obtain a matrix is equal to matrix 1 0 0. First row which is same as I3, but in second row we take one operation R2 plus 3R1, R2 plus 3R1, multiply row first by 3 and add it to row 2. 3 into 1 3, 3 plus 0 3, 3 1 0 0 0 1. This is elementary matrix. Okay. This is the solution of our problem. Second example, let A is equal to matrix 1 0 0 0 1 0 0 0 1.5. This is the matrix elementary EPS Y. We clearly see that row first is 1 0 0, which is row of identity matrix. 0 1 0, the second row is also a row of identity matrix, and in third row we clearly should seen that this 1 by multiply by 1.5, that is row 3 multiply by 1.5. Therefore this is an elementary matrix. Yes, it is. The matrix A is obtained from I3 by multiplying its third row by 1.5. Multiply third row by 1.5, you get this matrix. Next example, let A is equal to matrix 0 0 1 0 1 0 1 0 0 is the matrix elementary EPS Y. Okay, this is a matrix, and this is a matrix obtained by if this is I3. You take 0 0 1 0 0 0 matrix I3. Second row Okay, but this third row is in the position of this, and that is this matrix A is obtained by interchanging matrix A is from I3 by interchanging therefore A is an elementary matrix of order 3 by 3. This is the solution of our problem. Okay student, I stop here with this problem. In next lecture we see some theorems on elementary matrices. So today I stop with this.